Okay, hello everyone. Welcome to the lecture on aldehydes and ketones. Okay, in this chapter, we're going to be talking about the reactivity of aldehydes and ketones, but specifically the reactivity of the carbonyl group of aldehydes and ketones, and even more specifically, the reactivity of the carbonyl carbon of an aldehyde and ketone. So you probably know that it's electrophilic due to induction and resonance. And we're going to be exploring the different reactions that we can do, taking advantage of the electrophilicity of that carbon. Here on the bottom of the slide are a couple of examples of basically the simplest aldehyde, which is formaldehyde, has 2 hydrogens instead of an R group on one side. And it's used as a preservative. And the simplest ketone, which is acetone with 2 methyl groups, and it's used primarily as a solvent. Here are some more examples of different aldehydes and ketones that exist in nature. You might notice after reading a few of these names and flavors that they tend to have a nice smell and a nice flavor. Right, so aldehydes and ketones are nice in that they tend to be very pleasant, and that's in contrast to other functional groups like amines and carboxylic acids that we'll talk about eventually. Additionally, aldehydes and ketones are very common in biological molecules. For example, here's 2 sex hormones, progesterone and testosterone, and they contain either 1 or 2 carbonyl groups of ketones in this case. Let's talk about nomenclature briefly. Remember that with nomenclature, we're going to be focusing on a certain functional group to talk about how to name that group as a parent. And in this chapter, we're going to be expanding our ability to name aldehydes and ketones. The same procedure is used. We identify and name the parent chain, the substituents, assign a locant, and put the name together in the end alphabetically. So the first thing to note is what is the ending or the suffix of the name. So for example, if you remember a 4-carbon chain, if it was an alkane, it would be called butane. So if instead one of the terminal carbons is an aldehyde, but it still contains 4 total carbons, we would name it butanal. And we get that by dropping the E and adding the AL suffix. The parent chain must include the carbonyl carbon, even if it's not the longest chain. For example, here, the parent chain is hexanal instead of an 8-carbon chain, which is possible if we were naming this as an alkane. But because the aldehyde group has priority, we need to include that carbon in the parent. So it's the longest carbon chain that includes the carbonyl carbon. When you're naming an aldehyde, by definition, that aldehyde is at carbon number 1 because it's always on the terminal end of a carbon chain. So in order to have the lowest number possible, it will always be carbon number 1. For that reason, it's not important to assign a locant to locate the aldehyde when you're naming it with the parent as an aldehyde, because it will always be at carbon number 1. When you're naming ketones, we're going to drop the E and add the O-N-E suffix. So we would pronounce this butanone. We do need to include the carbonyl carbon in the carbon chain, right? So we would want to look for the carbon chain that includes the carbonyl, and we want the lowest number possible for the carbonyl carbon. And because ketones the carbonyl is by definition not at a terminal carbon, because if it was at a terminal carbon, it would be an aldehyde. So when it's a ketone, the carbonyl is not at a terminal carbon. We are going to need the number or locant included in the name. So we wouldn't just name this heptanone, we would need to name it either 3-heptanone or heptan-3-one. Of course, if you have chiral centers, the configuration of the chiral center is always included in the name in parentheses at the beginning, followed by the rest of the name, right? This one is an aldehyde, so by definition, this is carbon number 1. This would be carbon number 2 and carbon number 3. So we have a chloro group and a phenyl group. C comes before P alphabetically, so it becomes R2-chloro 3-phenyl propanal, because it's the 3-carbon chain, right, for the parent. When the aldehyde group is directly attached to a ring, we name the aldehyde group just carbaldehyde. So it becomes cyclohexane, in this case, carbaldehyde. There are a few common names that IUPAC recognizes for simple aldehydes. For example, formaldehyde. The IUPAC name for this would be methanal, but more commonly it's called formaldehyde. Acetaldehyde is a common name, right? This would be ethanal if you were naming it the IUPAC way. And then benzaldehyde is also a common name that you guys learned before in the aromatic chapter. Let's do some practice problems for nomenclature. Remember, we're naming these as aldehydes or ketones. The aldehyde group, just so you know, has a higher priority than a ketone. So if you have both an aldehyde and a ketone, the ketone is a substituent, and it's called an oxo group. So that will help you with this one down here. Why don't you go ahead and pause it and do your best to come up with names for these three, and then we'll go over it. Okay, let's go over how to do the nomenclature. This one has a ketone, and we're looking for the longest carbon chain. That includes the carbonyl carbon, right? So that's going to be, if I count 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, it's the same either way, right? So we can kind of circle one of those, call this our parent, and it's going to be, since it has 6 carbons, it's going to be a hexanone. When I assign numbers, I want the lowest number for the carbonyl carbon. So I'm going to do 1, 2, 3. If I had started from this side, it would have been 1, 2, 3, 4. 4, 5, 6 then. So our substituents are just 1, right, in this case, an ethyl group at carbon number 4. So in putting this all together, we come up with 4 ethyl, since that's our only substituent, and now we add the parent, right, and this becomes a either 3-hexanone or hexan 3-one. I'm going to name it the second way, which is the newer IUPAC way. Okay, looking at the next one over here to your right, this one has an ether group and an aldehyde group. Ether groups have no priority, so the priority goes to the aldehyde. And we're going to be looking for the longest carbon chain. You might notice that these are the same group, so it's not going to matter which direction we circle. But we can circle maybe going up here. And again, with the 2 methyls, it doesn't really matter which one you pick. Okay, just circle 1 for the parent. Right? In terms of numbering, we're always going to start with carbon number 1 at the aldehyde carbon. So that becomes 2, 3, 4, 5, and 6. So we do still have 6 carbons, but now it's named as an aldehyde. So the parent becomes a hexanal. What are our other substituents? We have a methyl group over here, a methoxy group, right? You can even write those out if you want. So methyl, methoxy. Sometimes I do that when I have a lot of groups. And then a 1, 2, 3, 4, 5. So this is an isopentyl group. Okay, in terms of the alphabetical order, the I counts. So it's I versus M and M, right? M and M is a tie. But alphabetically, when we come, the O comes before the Y, right? So methoxy comes before methyl in the name. Okay, but either way, I'm going to do the isopentyl first, right? So putting this name together, we would go 2 isopentyl, right? Sorry, you guys can't see that very well. I'll move this up. 2 isopentyl. Now we have methoxy is next, right? So -2 methoxy. Okay, and next is methyl -5 methyl. So those are all of our substituents. Now comes the parent, right? And we said we were going to call this a hexanal. Remember, we don't need to put a locant 1 for the aldehyde. It's implied without that. Okay, the last one here is this compound that contains both an aldehyde and a ketone. The aldehyde gets priority. So 1, 2, 3, 4, 5. The aldehyde got priority, so it has the lower number, right? The ketone actually becomes a substituent, and we're going to call it an oxo substituent. We additionally have one more substituent, and that is this ring, right? And this is called a cyclopentyl. Okay. We also have a chiral center, so we might want to determine if that is R or S before we start to put together the name. If we look at the groups attached, we have a hydrogen pointing out at us. And then you have carbon, 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 so that's all a tie. This carbon has 2 oxygens attached, so it's going to be priority number 1. Right? This carbon has carbon, hydrogen, hydrogen, and this is carbon, carbon, hydrogen. So this is actually priority number 2, even though there's another oxygen. It's we look at the first line of difference, right? And carbon, only 1 carbon here, 2 carbons there. So it becomes 1 to 2 to 3, which is a clockwise rotation, but the 4th priority group is coming out at us, so it's actually S. Okay, so we're going to make sure to put that into the name. So it becomes S in parentheses. Now we start with the substituents. We have C versus O, right? The C comes first. So 3 cyclopentyl, 4 oxo, right? Now comes the parent, and we have a 5 carbon chain, right? So this is a pentanal. Okay, we are back to the slides. Moving on from nomenclature, we're going to start talking about preparation of aldehydes and ketones. This is not the first chapter where we've seen aldehydes and ketones. In previous chapters, they have come up in the context of other functional groups, such as reactions of alcohols in chapter 12. So these first reactions are review reactions from previous chapters, and it nicely tells you the section to look in if you have forgotten this reaction. But these are good reactions to have on flashcards, so make sure you remember these reactions as well. They're very relevant to this chapter because they involve aldehydes and ketones. So we can oxidize a primary alcohol using either PCC or other reagents, which I personally didn't cover, but you may have covered. The Des-Martin pyrrhodinane or the Swern oxidation is this other one. Okay, but you can just remember PCC oxidizes a primary alcohol to an aldehyde. Ozonolysis of alkenes provides aldehydes, particularly if the hydrogens attached to the sp2 hybridized carbon exist, right? In this case, both sp2 hybridized carbons have 1 hydrogen. So when that happens and we do ozonolysis and cleave this alkene, we end up with two aldehydes. If these two R groups are the same, right, there's symmetry here, then this is actually the same thing as that, and we don't need to draw it twice. We've also seen the synthesis of an aldehyde from a terminal alkyne, right? So this is a anti-Markovnikov hydration reaction that tautomerizes to an aldehyde. And we saw this last semester in chapter 9. And so you can think of it as a hydroboration oxidation of a terminal alkyne, analogous to hydroboration oxidation of alkenes, giving the anti-Markovnikov product. Because we worry about side reactions, we typically use a bulky borane. So instead of BH3THF, oftentimes here we'll see 9-BBN, right, which is a bulky borane for this particular reaction. We can also oxidize secondary alcohols. When we do, we get ketones. And you can use sodium dichromate to oxidize secondary alcohols, and you can also use PCC, similar to the synthesis of aldehydes from primary alcohols. Ozonolysis of alkenes can also produce ketones. That happens when the sp2 hybridized carbons have all carbon groups attached here, right? When there's two carbon-based groups and no hydrogens, when we cleave the double bond, we end up with ketones. And again, if all four of those R groups are identical, then there's only one product, which is the ideal case. We can also produce a methyl ketone from a terminal alkyne using acid catalyzed hydration conditions with mercury sulfate as a catalyst. This again was initially introduced in chapter 9, which is the reactions of alkynes chapter. It can also be thought of as a Markovnikov hydration of the alkyne to produce a enol that tautomerizes to a methyl ketone. The last reaction here in our review section is a Friedel-Crafts acylation reaction. We just learned this in the very last chapter, chapter 18. We learned that Friedel-Crafts acylation allows us to introduce an acyl group, right, which is a ketone based group, onto an aromatic ring. Okay, let's stop here, do a practice synthesis problem. And what I would like you guys to do is think of two totally unique ways to achieve this multi-step synthesis. And one of those methods must involve an aldehyde or ketone intermediate, and the other one does not need to. So go ahead and take a moment, pause it, think about if you can come up with two synthetic pathways to be able to convert this terminal alkyne to an alcohol. And at least one of those needs to involve a ketone or an aldehyde intermediate. Okay, so let's see if you guys came up with the same thing that I did. So we have two options. The first one I'm thinking about is totally review and has nothing to do with an aldehyde or ketone, which is that we could reduce this alkyne to an alkene, right? And then we can do an addition reaction to synthesize the alcohol. So that would involve an alkene intermediate, right, that I could then convert to the alcohol. So reduction of an alkyne to an alkene. In this case, we don't have to worry about this being cis or trans. So you could either use hydrogen with Lindlar's catalyst, which is a poisoned catalyst, or you could use the dissolving metal reduction reaction with sodium and liquid ammonia. This is very different from NaNH2, by the way. Notice the comma here, right? So this is sodium metal and liquid ammonia. Either one of those would reduce the alkyne to an alkene, particularly if we don't need to worry about stereochemistry of the alkene. And then from here, we need to do a hydration reaction. Added to this carbon is going to be an OH. Added to this carbon is a hydrogen. So that's overall a hydration because we overall add H2O with H and OH. And it's going to be an anti-Markovnikov hydration reaction. So you need to remember the reaction conditions to do an anti-Markovnikov hydration, and those are hydroboration oxidation. So in that reaction, because we're starting with an alkene, we'll just use BH3 instead of the bulky borane. And second step is sodium hydroxide and hydrogen peroxide. And again, that does anti-Markovnikov hydration of an alkene. The other option that does involve an aldehyde or ketone that I thought of is we know we can convert an alkyne, particularly a terminal alkyne, to an aldehyde or a ketone, right? Depending on if we do a Markovnikov or anti-Markovnikov hydration. In this case, because the oxygen is at the terminal carbon and it's a primary alcohol, it is better to form an aldehyde that we can then reduce to that primary alcohol. So our key intermediate is going to actually be an aldehyde, right? So we're converting this terminal alkyne to an aldehyde. Make sure you don't add or subtract any carbons. And then we're going to be reducing that aldehyde down to a primary alcohol. So the conditions to form an aldehyde from a terminal alkyne, those are hydroboration oxidation, because again, that's an anti-Markovnikov hydration that forms an enol that tautomerizes to an aldehyde. But instead of using borane, we're going to use the bulky borane. And we do that when we're starting with an alkyne. So 9 bbn in the first step and the same second step. And then reduction of an aldehyde to an alcohol. You can either use sodium borohydride or lithium aluminum hydride, right? So over the arrow, let's say sodium borohydride or lithium aluminum hydride would accomplish that reduction. Okay, back to the slides. Let's look at the reactivity of the carbonyl. So the carbon of the carbonyl, as I mentioned before, is electrophilic, right? It's electrophilic because through induction, the sigma bond electrons are being pulled towards the oxygen, creating a delta positive on the carbonyl carbon. And also through resonance, right? The pi bonded electrons are spending more time around the oxygen, or there's greater electron density around the oxygen than there is around the carbon. And we can see that through the fact that the true structure is a hybrid of these two resonance structures. And this resonance structure has a positive charge on the carbon, which overall means there's a partial positive charge on this carbon. So through both a combination of induction and resonance factors, the carbonyl carbon is electrophilic. So we're going to see reactions that involve a nucleophilic reagent reacting with the carbonyl carbon. When a nucleophile does an attack, it attacks at an angle. If you look at the nucleophile carbon oxygen, and the angle therein is about 109.5 degrees, because in the end, this is going to end up 109.5 degrees with this carbon being tetrahedral. Right now, this carbon is sp2 and trigonal planar, right? So the nucleophile will be able to attack from the top face or from the bottom face, same angle here, right? And with respect to the oxygen. And that will potentially produce a racemic mixture if these two R groups are not identical groups. In terms of the electrophilicity of aldehydes and ketones, and again, we're specifically talking about the carbonyl carbon's positive character, or how much positive character it has. The more positive character, the more electrophilic the carbonyl carbon. When we're comparing aldehydes and ketones, what we're going to see is that aldehydes are more electrophilic at their carbonyl carbon than ketones are. And the reason for this is twofold. The first reason is steric effects. Hydrogens are simply smaller than alkyl groups. And any sort of alkyl group here is going to have multiple atoms attached. Even if it's a methyl, it would still have 3 hydrogens attached, which is can sterically prevent a nucleophile from coming in and attacking this carbonyl carbon. So sterically, the carbonyl carbon of an aldehyde is more accessible than the carbonyl carbon of a ketone. The second factor is an electronic effect. The delta positive of an aldehyde is larger than the delta positive of the carbonyl of a ketone. And the reason for this is, remember that alkyl groups next to something positively charged are electron donating, right? They donate through hyperconjugation into the slightly empty p orbital on this carbon, helping to stabilize it. So the ketone has 2 stabilizing groups, and the aldehyde only has 1. So as a result, the positive character is larger on an aldehyde than a ketone. So for those 2 factors, aldehydes are more electrophilic than ketones. And when I say that, what I mean is that the carbonyl carbon of the aldehyde is more electrophilic. So because it's electrophilic, we're going to be treating it with a variety of nucleophiles. And the reactions can occur under what the book calls acidic conditions or basic conditions. And the mechanisms are different, which is why they go to the point of separating the 2 conditions and talking about the mechanism under acidic and basic conditions and generalizing it that way. So for example, we know that Grignard reagents attack aldehydes and ketones. And because the reagent is a strong base as well as a strong nucleophile, we're going to call those conditions basic conditions. Okay, so another example would be hydride. So the hydride of sodium borohydride or lithium aluminum hydride. Hydride is also a strong base as well as a strong nucleophile when it's attached to boron or aluminum. And so that reaction is also going to be considered under basic conditions. So under basic conditions, nucleophiles are strong, right? So generally base strength and nucleophile strength are correlated. So typically we're dealing with a strong nucleophile, and the strong nucleophile will likely have a full negative charge or a very significant negative charge. And because it is negatively charged, it's going to be less stable, higher energy, and more reactive. So the activation energy to then attack the carbonyl carbon of a ketone is pretty low because of the high energy intermediate, right? So it's able to do a nucleophilic attack of the carbonyl carbon directly. When that happens, we say we get the tetrahedral intermediate because it goes from trigonoplanar to tetrahedral. So that's one way of describing this intermediate. The intermediate has a basic oxygen with a negative charge. This is going to need to be neutralized before we can isolate the product. So we show water as the acid under basic conditions. And it would protonate the alkoxide to form a neutral alcohol that could then be isolated. So those are the 2 steps involved under basic conditions. Direct nucleophilic attack using the strong nucleophile, followed by proton transfer to form the neutral product. Okay, what about acidic conditions, right? The mechanism under acidic conditions is going to be different from the mechanism under basic conditions, even if the product is the same and the reactant is the same, right? The reagent that's used is different. It's an acid and not a base. And so the first thing we're going to do is a proton transfer, because when you treat a ketone with a strong acid, the lone pair on the oxygen can get protonated. That generates an even more electrophilic intermediate that can then be attacked by a nucleophile to form the tetrahedral product in this case. As the nucleophilic attack under acidic conditions will always involve an acid. So that's how you can know you're doing something under acidic conditions versus basic conditions. The nucleophile can be weak or strong. Like for example, you could be using HBr here. That's an acid, which will provide a proton, but bromide is a good nucleophile. Even though it's a good nucleophile, because we treated the ketone with HBr, which is an acid, that reaction is governed under acidic conditions, okay? The nucleophile can also be weak. So instead of HBr, let's imagine we used H3O+, right? If our acid was H3O+, we know that hydronium ion will transfer a proton to the ketone, generating this intermediate, and our nucleophile is then water. Water is actually considered a weak nucleophile, right? It only has a partial negative charge on the oxygen. But when we have a protonated intermediate, even a weak nucleophile like water can do a nucleophilic attack on the carbonyl carbon. So weak nucleophiles require an acid to what we call activate the carbonyl for nucleophilic attack. It is activated through protonation. Notice that the intermediate has a positive charge and not a negative charge. This is something I want you guys to start picking up on in this mechanism and subsequent mechanisms that we learn in this chapter and future chapters. When we have mechanism under acidic conditions, it's common that intermediates might have a formal positive charge or might be neutral. Under basic conditions, if we look at the previous slide, our intermediates are likely to be negatively charged or neutral. So one of the things that I want you to think about going forward is when I'm drawing a mechanism, am I doing the mechanism under acidic or basic conditions? And think about the type of intermediates you should be generating. Under basic conditions, you should have intermediates that have a negative charge or are neutral. Under acidic conditions, you should have intermediates that have a positive charge or are neutral. That can give you the idea of whether or not you're doing or approaching the mechanism in a reasonable way based on if you're forming the right sort of intermediates that are reasonable under the conditions of the reaction. Let's talk about the activation of the carbonyl that I was talking about that occurs under acidic conditions. So we talked about before the fact that the carbonyl carbon is electrophilic even without protonation of the oxygen, right? When we draw these two resonance contributors, we see there is a partial positive charge on the oxygen, right? As well as a partial positive charge from induction. Let's compare the resonance contributors, right, to the resonance contributors that form from the activated carbonyl after proton transfer has taken place. When we're looking at these two, and we know that the true structure is a hybrid of these two, but not just a 50-50 hybrid, right? It's a weighted hybrid according to stability of the two, in this case, two resonance contributors. So because this resonance contributor is neutral with no formal charge, and this resonance contributor has a positive and a negative formal charge, overall, this is a much more significant contributor, right? Not only does it have no formal charge, but it also, all of the atoms have an octet, whereas this carbon lacks an octet in this particular resonance contributor. So while this is a significant contributor, it doesn't contribute nearly as much to the overall hybrid as this first contributor. When we compare the resonance of the activated ketone or aldehyde, we see now that the true structure is a hybrid of these two resonance contributors. Notice that neither one is overall neutral. Both resonance contributors have one formal positive charge. So as a result, this one is less stable, higher energy, and contributes less significantly to the overall hybrid than this one did. As a result, this contributes a little more significantly to the hybrid than the second resonance contributor right up here. So this contributor and this contributor are the ones that show the formal charge on the carbon. And this is just a little bit more significant, right, to the overall hybrid than this one is, due to the fact that this is much more stable than this is, right? So as a result, there is more positive charge on the carbon after protonation of the oxygen. So that's what we mean when we say that the acid catalyzes or activates the carbonyl carbon for nucleophilic attack. It's just simply making a more powerful electrophile at that carbonyl carbon than would have existed prior to proton transfer. So let's think about the reversibility of some of these reactions. How are we going to know if the reaction is reversible? Well, one way to know is to look at the nucleophile, right? In this direction, we did a reaction under acidic conditions because we're treating the ketone with HCl, which is an acid. The nucleophile is chloride in the reaction, right? And that's why we see the chloride incorporated into the product. But in the reverse reaction, if we were going back to the ketone and HCl, then chloride would have to act as a leaving group. So in the forward direction, it acts as a nucleophile. In the reverse direction, it acts as a leaving group. So if the nucleophile is also a good leaving group, the reaction will be reversible. If the nucleophile is a poor leaving group, it will not be reversible. So for example, a Grignard reaction, right? So the reaction of a ketone or aldehyde with a Grignard reagent would be irreversible because the Grignard reagent is not a good leaving group, but chloride is a good leaving group. And so that's why we're using this reversible arrow for the reaction. When it's reversible, oftentimes the carbonyl component is favored at equilibrium. Let's do a conceptual checkpoint and draw the mechanism of this reaction, both in the forward and the reverse direction. So I'll give you guys a minute to work on this. Remember that we are working under acidic conditions, right? Because of the acid being used in the reaction. Okay, so we're going to be drawing the mechanism in both the forward and the reverse direction. So whenever I'm drawing a mechanism, I like to draw in all the lone pairs, right? So that I can potentially use them to start an arrow to draw the mechanism. And I'm also going to be drawing HCl and the 3 lone pairs on the chloride. So the first step, because we're under acidic conditions, is protonation of the oxygen of the carbonyl using the acid. Remember, we call this the activation of the ketone, generating the more powerful electrophile at this carbon. Chloride can then do a nucleophilic attack on this very powerfully electrophilic carbon. And I don't want to exceed the octet on that carbon, so I send electrons up to the oxygen simultaneously through resonance. When we draw out the product, we see that we have actually already arrived at the product. So that is the mechanism in the forward direction. So it starts off with proton transfer, followed by nucleophilic attack. Okay, what about in the reverse direction? Well, in the reverse direction, we're going to start with the product, which is the reactant in the reverse direction. And we're actually going to hit the same intermediate that we did in the forward direction. So when you're drawing a mechanism in reverse, whatever intermediate you had in the forward direction is also an intermediate in the reverse direction, right? So we know we're going to be generating this intermediate, and the way to do that is to do loss of a leaving group, right? So chloride can leave, and simultaneously we can use this lone pair to show a resonance arrow. That will get us to the same resonance contributor we showed in the forward direction. Okay, and then from here, we're going to be, again, generating the two reactants in the forward direction, which are the products in the reverse direction. So we can do a proton transfer. To get back to the ketone or aldehyde. In this case, since it says two R groups, I'm assuming it's a ketone, but it could also have been an aldehyde. And HCl. So in reverse, we did loss of a leaving group, followed by proton transfer. Right, and sometimes because we are adding a proton to our organic substrate, we call this a protonation. And when we are removing a proton from our organic substrate, sometimes we call this a deprotonation. Okay, let's go back to our slides and continue on. So in this chapter, we're going to be talking about nucleophilic addition reactions to aldehydes and ketones using a variety of different nucleophiles. We'll talk about oxygen nucleophiles, which include water, alcohols, and diols. We'll talk about sulfur nucleophiles, which are analogous to the oxygen-based nucleophiles, just with sulfur in place of oxygen. We'll talk about amine-based nucleophiles. So those are different types of amines. Specifically, we're going to talk about primary amines and secondary amines. Hydrogen-based nucleophiles, those you should be familiar with in our technically review reactions. So the addition of LAH or sodium borohydride to a ketone or aldehyde to do the reduction. And then carbon-based nucleophiles, this is a Grignard reagent that's also a review reaction. We can also use cyanide, and this new reaction, which involves this carbon-based nucleophile, which we call a Wittig reagent or an ylide. We're going to start off talking about oxygen nucleophiles. Specifically, the first oxygen-based nucleophile we're going to use is water. Water can react with aldehydes and ketones to produce what's called a hydrate. A hydrate is a carbon that has two alcohols attached to it. You might also think of this as like a geminal diol. The reaction is reversible, and in most cases, the equilibrium favors the ketone or the carbonyl-based component with some exceptions. Okay, so the ketone or aldehyde usually is favored by equilibrium with some exceptions. And the exceptions basically involve unstable ketones or aldehydes. So if you're using a particularly unstable ketone or aldehyde, then the equilibrium might favor the hydrate, but typically it does not. And the reaction is catalyzed by either acidic or basic conditions that will significantly enhance the rate of hydrate formation. Let's look at the mechanism under both basic and acidic conditions. Under basic conditions, right, we are going to draw a mechanism that is consistent with basic conditions that we talked about before. So under basic conditions, the first step is the use of a strong nucleophile, such as hydroxide, to do a nucleophilic attack on the electrophilic carbonyl carbon. At the same time, we'll draw a resonance arrow to avoid exceeding an octet on this carbon. That gets us our tetrahedral intermediate that needs to be protonated to form a neutral product, in this case, the hydrate. And because water, hydroxide, even though you might not think of it as a good leaving group, it is a good enough leaving group in these particular conditions such that the reaction is reversible, and we can kick out hydroxide in the reverse direction as a nucleophilic attack. Under acidic conditions, remember the mechanism is different, and the mechanism that we propose should be consistent with the acidic conditions that are employed in the reaction. If we are using water under acidic conditions, the likely acid is hydronium ion. So hydronium ion can protonate the oxygen of a carbonyl, again activating this carbon towards nucleophilic attack. Water can then act as the nucleophile to do the nucleophilic attack, forming the tetrahedral intermediate. At this point, we have an intermediate that still needs to lose a proton in order to become neutral. Sorry, I am going to need to stop for a second. Oh, looks like my husband's going to answer. My son is screaming something, so. Okay, so we still have a need to do a deprotonation or proton transfer to remove this proton to get the neutral hydrate product, right? So this reaction actually has 3 steps. We need an additional proton transfer because our nucleophile is neutral and contains 2 protons, and one of those must be removed in order to have a neutral oxygen in the product. Either way, the reaction is still reversible under both acidic and basic conditions. In this case, the reverse of the nucleophilic attack would be the loss of a leaving group of water, and water is a good leaving group, so it's very reasonable to think that this step is reversible. Again, this is a slide that talks about you need to keep the following in mind when drawing mechanisms. Under acidic conditions, a mechanism will only be reasonable if it avoids the formation of strong bases, right? So just remember that a strong base cannot exist in an acidic environment, okay? And a strong acid, by contrast, can also not exist in a basic environment, right? So we wouldn't want to generate something that is unreasonable in a mechanism. Let's talk about when we use an alcohol as a nucleophile. You can think of alcohols as similar to water, right? They are very similar to water. They're neutral, oxygen-based nucleophiles. But when we use an alcohol instead of water as the nucleophile, we don't end up with a hydrate where we have 2 OH groups. Instead, we end up with something we call an acetal, which has 2 OR groups. So whenever you have basically 2 ether groups, right, 2 OR groups attached to the same carbon, we are going to call that an acetal. We can form that from a ketone or an aldehyde in the presence of, now we're going to need 2 equivalents of alcohol to form the acetal. Water is one of the products, and a strong acid catalyst is required for the reaction. So catalytic strong acid such as sulfuric acid, or even possibly para-toluene sulfonic acid, can be used as the catalyst to form an acetal. Notice the reversible arrow, right? So just like hydrate formation is reversible, acetal formation is reversible. So we need to utilize conditions that will favor the direction that we want for the equilibrium. So for example, one of the easy ways of manipulating the equilibrium is through the use of the fact that water is a product in acetal formation. If we remove water from the reaction mixture as it generates, that is going to drive the equilibrium forward to produce the acetal. If we add a bunch of water to the reaction mixture, that's like adding an excess of one of the reactants in the reverse direction. That will drive the equilibrium back towards the reactants. So we can either use a large excess of one of the reactants to get the reaction to go the direction that we want, right? Or we can remove one of the products. So those are things that we would have to do if we wanted to manipulate the equilibrium in this reaction. Let's look at the mechanism of acetal formation. So I mentioned before that a catalytic amount of strong acid is required. So you should be thinking about the fact that this mechanism should be consistent with acidic conditions, right? What sort of intermediates do we typically see under acidic conditions? Our intermediates should either be neutral, right, such as this one, or have a positive charge, for example, this one. Do you see any intermediates that have a negative charge? The answer is no, right? That is typically not consistent with mechanisms under acidic conditions. So that's something we want to pay attention to. In addition, look and see if you can find any intermediates with more than one positive charge, right? So 2 positive charges, right? So here we have 1 positive charge, 1 positive charge, neutral, 1 positive charge, 1 positive charge, 1 positive charge. Notice that we never found an intermediate with more than 1 positive charge. That's very important, and I want you to think about avoiding the formation of intermediates with more than 1 positive charge. Why do we avoid the formation of those sort of intermediates? It's because if an intermediate has 2 positive charges, it's really unstable, and it's unlikely to form in a reaction mixture. Anything that's really unstable will be a high energy intermediate with a large activation energy to get to that intermediate. So it's going to slow the rate of the reaction down if we have to generate a high energy intermediate. So high energy intermediates, like those that have more than one of the same charge, should be avoided. It's just not very reasonable to generate something like that in solution, because we always have to think about the energetics of a reaction, right? And climbing the energy barrier, right, to get to a high energy intermediate is very difficult. Okay, all of that being said, let's go ahead and go through the steps. So the first step under acidic conditions is proton transfer, right, where we're protonating the oxygen of the carbonyl of an aldehyde or ketone. From there, we have a very electrophilic carbon that generates. So even a weak nucleophile, such as an alcohol, can do a nucleophilic attack. Once we do that nucleophilic attack, we've got a tetrahedral intermediate. That tetrahedral intermediate has an oxygen that's positively charged. So if we want to do anything else with this, the first thing we need to do is remove the proton to make this neutral. Because, for example, you might be thinking, I would really like to protonate this oxygen so that this will be a good leaving group, right? It will be water, which is a good leaving group if we protonate this. But we cannot do that right away, because if we did that right now, we would have an intermediate with 2 positive charges, and that's unreasonable. So it makes much more sense to deprotonate the positively charged oxygen and then add a proton to the other oxygen, right? A series of proton transfers that avoids having an intermediate with 2 positive charges is very reasonable. Notice that they're just sort of using generic acid, which would be H attached to A with a positive charge, and this is sort of their generic base. You could use real acids and bases if you want, or it's also okay to use generic acids and bases. The real acid would be the protonated alcohol, right? So that's what this would really be. And the real base is just the alcohol, so another alcohol. But it's okay, again, to use these sort of generic descriptions of an acid and a base as well in your mechanism. So once we've deprotonated this oxygen, we're going to go ahead and protonate this oxygen. My goal is to get rid of this as water, right? This is where the water comes from. And I want this OR group because I see it in my product, right? So I need 2 OR groups, and I need to remove this, right, and produce water. So if I protonate this, it becomes a great leaving group, and now it can leave in the form of water as the leaving group, right? And we can use this arrow to sort of help push the water out for the loss of the leaving group step. That generates the most stable resonance contributor directly if we include this arrow. So that's advantageous for just simply drawing fewer steps. From here, again, this carbon is very electrophilic because it's attached to a positively charged oxygen. So it makes sense that a second alcohol would come in and do a nucleophilic attack, right? form the intermediate where the oxygen is positively charged. We call that an oxonium ion. And after deprotonation, it will be the neutral OR group. And since there's two of them, we can call this an acetal. You might be thinking, why doesn't the water attack, right? Instead of the alcohol in this place. And the water can attack, but when it does, it just goes back. And these steps are reversible. So water can attack, it can get kicked right back out. Eventually, if we remove water from the reaction mixture, that will drive the equilibrium to where the alcohol then attacks, and eventually we get the acetal. So again, did you notice that all of these steps have this reversible arrow, right? And that means that the entire thing is reversible. So we have to manipulate the equilibrium to get it to go in the direction that we want. Okay, so acetal formation is an equilibrating process. Equilibrium can favor the acetal product, but it doesn't favor the acetal product for ketones. Instead, the ketone is typically favored at equilibrium. So how do we then form acetals from ketones, right? We would have to really manipulate the equilibrium to favor the products, particularly with the ketone, because they're not favored normally. One of the things that can help is forming, instead of an acyclic acetal, we could form a cyclic acetal. To form a cyclic acetal, instead of using two separate alcohol molecules, we can use a diol. When we use a diol, the two OH groups are tethered to the same carbon-based chain. As we go through the hemiacetal intermediate to the acetal, right, we now have a cyclic acetal product, which is favored at equilibrium. So it's easier to form. So that's an advantage. I didn't point out when we were looking at the acetal mechanism, this hemiacetal. Think of hemi means half. So we're like halfway to the acetal. It's the carbon with an OR group and still one OH group. That's the half or hemiacetal. And it's formed en route to the acetal. Acetal formation, we talked about the fact that it's reversible. It can be controlled by adding or removing water from the reaction mixture. So to favor acetal formation, water needs to be removed, right, from the reaction. And in reverse, then we would add a very dilute acid solution where there's a lot of water around to get it to go back to the aldehyde or ketone. Because it's a reversible reaction, you can think about potentially using an acetal as a protecting group for the carbonyl of an aldehyde or ketone. We can place it on, do some other reaction we want to do, and then remove it later. Why? How is this an advantage, right? Well, we know that the carbonyl carbon of an aldehyde or ketone is electrophilic. For example, it could be attacked by a Grignard reagent or a hydride reducing agent. But once it forms the acetal, this carbon is no longer as electrophilic as this carbon. So as a result, this acetal is actually pretty stable under basic conditions. So it's not going to react with a Grignard reagent or a hydride reducing agent. So that can be an advantage if you need to do one of those reactions and you don't want to touch your ketone or aldehyde in the reaction. So let's look at an example. Consider how we would reduce this ester to a primary alcohol in the presence of a ketone. This is actually very difficult because ketones, particularly specifically the carbonyl carbon of a ketone, is more electrophilic than the carbonyl carbon of an ester. That's because the oxygen is actually donating electron density, helping to stabilize the positive charge on this ketone. So as a result, this carbonyl carbon is more stabilized than this one is. So this carbonyl carbon is more electrophilic, and it's very difficult to then reduce an ester, which is less electrophilic and less reactive, than a ketone, which is more electrophilic and more reactive. So if we wanted to do this, we would need to utilize a protecting group for the ketone. So what we could do is form a cyclic acetal using a diol. a strong acid catalyst and potentially removing water from the reaction mixture to favor the acetal addition. At this point, this carbonyl carbon is protected, right? Now we could reduce our ester. To reduce an ester, we need to use lithium aluminum hydride. And then we can remove the acetal. Under acid conditions, right, dilute acid conditions, that's how we remove the acetal protecting group. So this would not only protonate the alcohol, right, after the lithium aluminum hydride reduces this carbon, so it provides the proton in the acidic workup for the lithium aluminum hydride reaction, but in addition, acidic conditions remove the acetal group and reveal the ketone again. So we're able to effectively reduce the ester without touching the ketone by protecting and then deprotecting the ketone. Let's talk a little bit more about that hemiacetal intermediate that forms sort of en route to an acetal. Typically, it's hard to isolate a hemiacetal because it would continue reacting either to go to the acetal or in reverse back to the aldehyde or ketone. So while it's very difficult to typically isolate a hemiacetal, it's possible to isolate cyclic hemiacetals. Those tend to be more stable than acyclic hemiacetals, particularly with a stable ring size, like a 5 or 6 membered ring. So for example, this is a cyclic hemiacetal, right? There's a ring here, and there's a carbon with both an OR group and an OH group. So we call this a hemiacetal, right? Because of the ring, the hemiacetal is favored at equilibrium. If there hadn't been a ring, it would have gone back, and the reverse would have been favored at equilibrium. To generate a hemiacetal, what we need is a cyclic hemiacetal. To be specific, we need a carbonyl, and we need an alcohol that's actually within the same molecule as the carbonyl. That will allow us to form a cyclic hemiacetal. Because there is no second alcohol, right? There's only one. So we stop at the hemiacetal. We don't go on to a acetal product. An example of this formation of a cyclic hemiacetal is in carbohydrate chemistry, right? So for example, glucose, when it's drawn in its open chain, has an aldehyde, and it has a variety of hydroxyl groups or alcohol groups attached to a 6-carbon chain. Specifically, this oxygen can attack the carbonyl carbon of the aldehyde to form a cyclic hemiacetal, which is, you can then draw as a chair conformation because it's a 6-membered ring. Notice how all the OH groups, aside from this one, are all equatorial. So this is a very stable ring, and it's actually favored at equilibrium. So the majority of glucose molecules exist as their cyclic hemiacetal, and very low percentage exists as the open chain aldehyde form. Okay, let's do some practice, and we're going to draw a reasonable mechanism for this transformation, right? Hopefully you recognize that this carbon has 2 OR groups attached to it, right? So we call this an acetal. So really this is just intramolecular acetal formation where we're using a ketone and 2 alcohols that happen to be attached to the ketone, right, on the same carbon chain. Catalytic acid is being used, so make sure your mechanism is consistent with acidic conditions, and we should be producing a molecule of water in this reaction as well. So go ahead and stop and see if you can draw a reasonable mechanism, again trying to follow those acidic conditions. Okay, so let's start drawing our mechanism. We have, whenever I draw a mechanism, I like to draw in all the lone pairs, right? That helps me draw the mechanism. And again, catalytic acid, right? Sulfuric acid means that there'll be water around, so we can generate some hydronium ion to use as our acid source in this reaction. So I'm going to draw some hydronium ion here. Okay, and let me think about what I should protonate. Should I protonate the oxygen of the alcohol or the oxygen of the ketone? Right? Both can be protonated and both are reversible, right? So what we're going to draw is what helps us get to the product, not necessarily what's happening in solution, because the proton can go onto this oxygen and come right back off, right? And that's reversible. Same thing with this one. Same thing with this oxygen as well. So we're actually going to draw this one because this one helps us get to the product. Right? And so that's why we're doing that, not because it's the only thing that's happening in solution. So remember, under acidic conditions, we should protonate the carbonyl. Don't forget all those lone pairs. Okay, so now this carbon is very electrophilic, right? And we can do a nucleophilic attack using one of the lone pairs on our oxygen. Right, this is probably going to give you an idea of the size of ring you should form. It's going to be forming a 5-membered ring. 1, 2, 3, 4, 5. Okay, so now I've drawn the product of the nucleophilic attack. Right? Notice that I have a positive charge here. I need to get rid of that before I can move on and protonate something else. Right? If I want to protonate one of these other oxygens to make a good leaving group, I need to do that after I deprotonate here to avoid forming an intermediate with more than one positive charge. So something can come in and remove this proton. Right? It could be, you could use your generic A with 2 electrons base, or in this case, I'm just going to use water, which is a more specific base for this reaction. So water is going to act as my base, and I'm going to deprotonate that proton, get a neutral intermediate that I can then protonate somewhere else. Okay, notice that I did now get to my hemiacetal intermediate. So en route to an acetal, I should make a hemiacetal, right? So that can let me know that I'm on the right track with getting where I want to go. Okay, so what I need is that this oxygen is going to be bonded to that carbon, right? To make my other ring, I need this oxygen, right, to be bonded here, okay? So what I'm going to try to do is get rid of this as water. Okay, so I need this to be a good leaving group. I want it to, I can't kick it out right now. Because if I kick it out right now, it's going to be hydroxide. That's going to generate a strong base under acidic conditions. That's not possible. So I need this to be protonated first, become a good leaving group, and that will avoid forming a strong base when I kick it out. So I'm going to use some hydronium ion to protonate that oxygen. Okay, that gets me there. Now I can kick it out. I'm going to use one of these lone pairs to help me push it off. Right now I have finally lost my water molecule. Right, so I've produced the water molecule that I know I need to produce in this reaction. Okay, that gets me to this intermediate. Remember, any carbon that's double bonded to an oxygen that's positively charged is very electrophilic. So right now it's ready to receive the nucleophilic attack of the lone pair from the hydroxyl group. That will get me to my penultimate intermediate. Where I am going to nearly be at the product. I just need to do one last proton transfer to get to the product. So I'm just going to draw in a water molecule and show that deprotonating to get to the product, and that regenerates catalytic H3O+. Right? So if it's a catalyst, that means we can use it and we regenerate the acid in the reaction. Okay, so that is the mechanism. Okay, going back to the slides, let's move on and start talking about nitrogen nucleophiles. So with nitrogen-based nucleophiles, over the arrow, we're going to see some sort of amine, right? And we're going to classify them as either being a primary amine or a secondary amine, right? And when we're using a primary amine nucleophile with an aldehyde or ketone, typically acid catalyzed conditions are employed that will enhance the rate of the reaction, and we'll talk about that. This reaction produces water as a product, right? So, and it's also reversible. So again, we can use Le Chatelier's principle to manipulate the equilibrium. But when you react an aldehyde or ketone with a primary amine, you end up with what's called an imine product. An imine product is characterized by a carbon-nitrogen double bond, as you can see here. How is the imine product formed, right? Let's look at this first step, because this is really, really strange. I want you to think about this and think to yourself, that is really, really strange, right? That is not what Dr. Gilly has taught me to do. Because remember, we said this reaction is going to occur under acidic conditions, right? Notice the catalytic acid we saw in the over the arrow. So the first step that they're showing is nucleophilic attack of the amine base, or the amine nucleophile, excuse me. And it's attacking the electrophilic carbonyl carbon. But look at this negatively charged oxygen, right? You should be seeing red siren should be going off in the background, right? Fireworks should be going off. You should be going, oh my gosh, how can we generate a negatively charged oxygen under acidic conditions? She told me to avoid that. Okay, and that's true. This sort of intermediate with a negatively charged oxygen should not be formed with oxygen nucleophiles, but can be formed with nitrogen-based nucleophiles. This is a high energy intermediate, okay, because of this negatively charged oxygen and the positively charged nitrogen. Two charges, right, within the molecule. They're not next to each other, stabilizing each other. This is a very high energy intermediate, and it will be immediately protonated by the acid in solution. Okay, but it does form, and we're going to talk about why we believe that it does form in this mechanism when it does not form in mechanisms that involve an oxygen-based nucleophile. But for now, we're just going to draw the nucleophilic attack without first protonating the oxygen of the ketone or aldehyde. That will generate a tetrahedral intermediate with an oxygen with a negative charge. That's not going to last very long under acidic conditions. That will be immediately protonated. And then we can deprotonate the amine to get a neutral intermediate, which they call a carbonylamine. From here, the goal is to get rid of this as water, right? So we're going to protonate this to make a good leaving group, and then kick it out, use the nitrogen's lone pair to help kick the water molecule out, right? And that forms what we call an iminium ion. That just needs to be deprotonated to get to a neutral imine product. Notice that all of these steps are, again, reversible, just like acetal formation, which means that we can go back, right, in the mechanism with a series of proton transfers. And where it says loss of a leaving group, in reverse, it would be a nucleophilic attack. And reverse of nucleophilic attack is loss of a leaving group. So we can reverse this entire mechanism and go back and hit all of the same intermediates that we do in the forward direction. Those are formed going back in the reverse direction. So you can go ahead and try drawing the mechanism in the reverse direction, right? Again, proton transfers are proton transfers, and loss of a leaving group and nucleophilic attack steps are the opposite of one another, right? When we're thinking about reversing the reaction. Okay, let's talk more about that first step because it is very weird, right? And how can we explain what's going on and why is this mechanism different with an amine nucleophile compared to an alcohol-based nucleophile? Well, with an amine nucleophile, remember that amines are more basic than alcohols, right? Amines are, we think about extractions, right? Amines are our most basic functional group, and they react with acids to form ammonium ions. Okay, so any acid catalyst that's added to this particular reaction mixture, the acid is going to protonate the amine and form an ammonium ion. The pKa of ammonium ion is only about 10. It's not that strong of an acid. This is not a strong enough acid to donate a proton to the carbonyl of a ketone or an aldehyde. And if you want to see a more in-depth explanation of why we don't protonate the carbonyl when we have a nitrogen-based nucleophile, watch this YouTube video that I generated. And it's, you can, if you're looking at the PowerPoint slides, you can just play the video, or you can go to YouTube and follow this link to visualize the video. I go through drawing out the mechanism step by step, and also an in-depth pKa analysis of that first proton transfer step to explain why we draw the mechanism the way that we do. Okay, for now we're going to move on and say that some pH studies have been done for this reaction, specifically imine formation. And what's found is that the ideal pH is around 5. Okay, so the rate goes down if the reaction is too acidic or not acidic enough. So what's the reason for that, right? If the reaction is too acidic, then all of the amine in solution will be locked up as the ammonium ion. And if that's the case, there's no nucleophilic amine to do the nucleophilic attack step in the mechanism. If you don't have enough acid, right, meaning we're at a higher pH, then we don't have any protons, right, there to help catalyze the reaction and do all the protonation steps that you saw in the mechanism. So basically, it is useful to have a slightly acidic environment, but too acidic is not ideal, because then all of your amine, right, will be converted to ammonium ion. And ammonium ions don't have a nucleophilic lone pair on the nitrogen to do a nucleophilic attack. Okay, oops, here we go. When you have a secondary amine over your arrow, what you end up with is an enamine, right? Notice that it's a different structure than an imine. right? So primary amines form imines, and secondary amines form what we call enamines. Okay, so that's the difference. And this name is generated from the ene is the alkene, and then amine. So think of like enol. This is an enamine. Same conditions, right? A slightly acidic environment is ideal, just like imine formation for enamine formation. And in fact, the mechanism is identical to imine formation, except for the very last step. Let's look at the mechanism. So secondary amines, just like primary amines, can do a nucleophilic attack, generating the tetrahedral intermediate with a negatively charged oxygen, which would immediately be protonated under a pH 5 environment. From here, water can, or some other base can remove this proton. So this could be water or an amine base. Could remove this proton to form the neutral carbonylamine. The goal now is to get this OH group to be a good leaving group. So we will protonate it. Again, this would not be possible without an acidic environment. So protonation to get a good leaving group, which can then leave. That forms an aminium ion, right? This last step is the difference between forming an enamine and an imine. Because there are no hydrogens attached to the nitrogen, we cannot deprotonate, right, the hydrogen if there isn't one there. So as a result, the proton that gets removed is on the alpha carbon to the carbon forming the imine. So if the base comes and takes this proton, electrons can swing over to form an alkene, and we'll get a neutral nitrogen atom. So that's how we get to a neutral species. Remember that with a primary amine, there will be a hydrogen attached to the nitrogen that can be removed in the last step to form an imine. If you use a secondary amine, both of the groups attached to nitrogen are alkyl groups. So there is no hydrogen that can be removed here. Instead, a hydrogen is removed on the alpha carbon, and electrons swing up to the nitrogen to form an enamine product. I have a video on YouTube as well on the formation of enamines that you can watch if you want to see me draw out the mechanism step by step. Okay, let's move on to the Wolff-Kishner reduction. The Wolff-Kishner reduction is a two-step synthesis, and it converts a ketone all the way down to a methylene or an alkene. The first step is the formation of what we call a hydrazone, right? And it utilizes hydrazine as the nucleophile. So NH2 bonded to NH2 is called hydrazine. And the product here is called a hydrazone because of the double bond, kind of like the one of a ketone. The conditions are the same as imine formation, right? Catalytic acid, we need to remove water in the reaction to drive the equilibrium forward. You can think of this as entirely analogous to imine formation. The difference is that instead of an R group, we have an NH2 group here. So instead of adding a primary amine, we added hydrazine, right? But otherwise, it's exactly the same thing as imine formation. From there, the second step involves strong base, potassium hydroxide, under aqueous conditions with heat. And what we do is we lose nitrogen gas, and we end up with a carbon that's been fully protonated and reduced, right? So we're able to completely essentially reduce the carbonyl all the way down to an alkene using this Wolff-Kishner reduction. This reaction is notable because of the basic conditions. We've actually seen the reduction of a carbonyl to an alkane before. If you recall, the Clemmensen reduction from chapter 18 reduces a carbonyl all the way down to a CH2 group, but it does so with zinc-mercury amalgam and HCl conditions. So that reaction occurs under acidic conditions, and this one is occurring under basic conditions. So these can be the choice of the reaction that you do depends on if your substrate is more sensitive to acid or base, you might utilize the other reaction. Let's look at the mechanism of the Wolff-Kishner reduction, specifically the second step, right? The first step is entirely analogous to imine formation. The second step, again, is the step that has potassium hydroxide and water and heat being added to the reaction. So since we have hydroxide, we can deprotonate one of the hydrogens attached to the nitrogen. You can draw a resonance contributor using the allylic lone pair to show that the partial negative charge is delocalized on this nitrogen and also this carbon. You can see that this particular resonance contributor, we start to notice N2, right? So we're almost to nitrogen gas being formed here. The carbon anion can be protonated using water. We can get another deprotonation with a second hydroxide, right, at the last hydrogen attached to a nitrogen atom. That gives us a negatively charged nitrogen, which can essentially eliminate this alkyl group, forming nitrogen gas, and a carb anion, which is very basic, so it would be immediately protonated by any water in solution to form an alkane. So this is a really interesting reaction. The equilibrium is going to be driven by this particular step, right? The loss of nitrogen gas. The nitrogen gas will bubble out of solution and it will drive this step, making the step irreversible. And of course, this proton transfer with a huge difference in pKa between water and an alkane is also an irreversible step. I have a YouTube video on the Wolff-Kishner reduction showing the mechanism drawn out, right, step by step. If you want to watch that as you practice drawing the mechanism, that would be advantageous. So you can, again, look at the PowerPoint slides I provided to you on Canvas, or just use the link to get to YouTube directly. Okay, so some similarities, right, between the mechanisms that we discussed. In general, under acidic conditions, the reaction intermediates should either be neutral or have one formal positive charge, right? The only exception is that very first nucleophilic attack that occurs with nitrogen-based nucleophiles. That one is drawn that way because of difference in pKa values between ammonium ions and protonated ketones compared with hydronium ion and a protonated ketone. And again, watch the YouTube video for a more in-depth analysis of that pKa difference. Okay, let's practice. I would like you guys to think about how you can draw either the missing product, right, or the missing reagents for these two reactions. Think about the fact that we're using a nitrogen-based nucleophile because we're in that section, right? So ask yourself, am I forming an imine? Am I forming an enamine or something similar? Okay, go ahead and pause the video and do your best, and then we'll go over it. All right, let's go over it. So if you notice what type of amine we have here, this is a secondary amine, right? Notice this is a secondary amine. So when we use a secondary amine, do we get an imine or an enamine, right? We get an enamine. So I already know that I'm going to be forming an enamine. So the reaction is going to be between this nitrogen and the electrophilic carbon. This water, or this oxygen, will be removed as water, right? So I'm going to think about the ring size, right, by counting from the nitrogen to the carbonyl carbon, because that's where the nucleophilic attack is going to happen, right? The first step is nucleophilic attack on that carbon. Okay, so I know that I'm going to be forming this 5-membered ring, right, with the nitrogen atom in the ring. So I can kind of start there, right, just sort of sketch a nitrogen containing 5-membered ring. Okay, and let's think about, we are going to be essentially initially forming a double bond, right? So if we can, you can sort of count 1, 2, 3, 4, 5. Okay. Attached to the nitrogen is a methyl group, right? So I can go ahead and add a line there for the methyl group. This hydrogen will be removed, right? Initially, a double bond occurs between 1 and 5, right? 5 has a tert-butyl group attached to it. And then a proton gets removed from the alpha carbon, which is carbon number 4, right, to generate the alkene. And this is the enamine. So think of it as carbon number 4 is the alpha carbon. That's where we lose a proton in the last step, right, to form an alkene, and then we get an enamine. Okay, and you can draw out the mechanism if you can't see how to form that product. All right, what about this, right? Let's think about what the heck got added here. Okay, that doesn't look like something I recognize necessarily, but I can still imagine that this is kind of like an imine, right? They're telling me it's not called an imine, it's called an oxime, but I think of it as kind of like an imine anyway. So if I use a primary amine, I would be able to form an imine, right? That would be NH2 attached to R. My R in this case is OH, right? So that's kind of like my primary amine, where R in this case is OH. That forms something like an imine, but because this isn't an R group, they named it something else called an oxime. Any sort of imine or enamine or oxime or hydrazone formation will use an acid catalyst, and we will lose water in the reaction mixture. And I'm going to take a little break because it's exhausting lecturing for this long. See you in a minute. All right, I'm back. Had some water. Hopefully you took a break too. You're not trying to watch this all in one go. Research shows that we can digest material in smaller increments much better. All right, let's go back to the slides. And we are on the 19.7 hydrolysis of acetals. So we've been talking about the fact that a lot of these reactions are reversible. Specifically, hydrate formation is reversible, acetal formation is reversible, imine, enamine formation is reversible. So all of these reactions can be drawn in the reverse direction. They're still acid catalyzed, right? But in reverse, we add water. So typically a dilute acid solution might be used in order to have a lot of water around and some acid to catalyze the reverse reaction. Whereas in the forward direction, when we used alcohols in the carbonyl of a ketone or aldehyde to produce an acetal, we tried to remove water from the reaction mixture. So it's simply the reverse. And note that under basic conditions, acetals are stable, which makes it a great protecting group for ketones and aldehydes under to make this carbon unreactive under basic conditions. Okay, so let's look at the mechanism of the hydrolysis of an acetal, or the reverse acetal formation. If you compare this slide, like if you printed it out and compared it to the formation of an acetal, what you would see is that the exact same intermediates are formed, right? We, even going in reverse, we form the hemiacetal en route to back to the ketone, right? So the same exact intermediates are formed. That's really, really important that you understand that when we're drawing a mechanism in reverse, we're forming the same intermediates, just going the opposite direction. Proton transfers are still proton transfers, but nucleophilic attacks become loss of a leaving group, and loss of a leaving group become nucleophilic attack. Remember, I said that the reverse reaction is catalyzed under acidic conditions. So all of our intermediates should have either one formal positive charge or be neutral, For example, the hemiacetal is neutral, but not contain two positive charges as that's too unstable to form, even in the reverse direction. So in reverse, we can proton transfer to protonate one of the oxygens of the OR groups of the acetal. When you protonate it, it becomes a good leaving group, and we can go ahead and kick out the alcohol leaving group. That gives us the carbon double bonded to an oxygen with a positive charge. We know that this carbon is very electrophilic. So there's a lot of water around, right? Water is going to do a nucleophilic attack. After it does a nucleophilic attack, we have a positively charged intermediate. We need to remove that proton before we can protonate the other oxygen to get rid of it. So first we remove the proton, get our neutral hemiacetal intermediate. Then we can add a proton to the other oxygen, creating a good leaving group again. We can then kick it out, and we are almost at the ketone product. We just need a final proton transfer to get to the ketone product. So again, all of these steps are reversible, and this reaction is favored under conditions where we have an acid catalyst and a lot of water around. Imine and enamine formation is also reversible with an acid catalyst and a lot of water around. They will go back to the ketone or aldehyde and the either primary or secondary amine, depending on if it's an imine or an enamine. Let's talk about sulfur nucleophiles. We can form what's called a thioacetal, right? So it's basically an acetal where the oxygens are replaced by sulfurs. That could be formed from a ketone or aldehyde and two thiols. And it's reversible, right, with water as the product in this direction. Just like we can form a cyclic acetal, we can form a cyclic thioacetal. And the main advantage of this is the fact that we can do what's called a Raney nickel reduction of the carbon of the thioacetal. So specifically, carbon sulfur bonds are labile to mercury. And Raney nickel is a mercury aluminum amalgam, and we can reduce this bond and replace it with a hydrogen from an acid. So Raney nickel is acidic condition, so it's an alloy that's been impregnated with acid. So acid is available to protonate anions that generate at this carbon, and we end up with an alkane. So overall, if we form a cyclic or acyclic thioacetal, followed by Raney nickel, we'll be able to reduce a ketone all the way down to an alkane. So you might have noticed at this point that we have now generated a third or learned a third reaction where we fully reduce the carbonyl of a ketone or aldehyde all the way down to an alkane. So this is just a conceptual checkpoint to see if you can remember and list those reactions, right? There are 3 different ones that reduce a carbonyl all the way down to the alkanes. And then ask yourself, how are these reactions different than the reduction of a ketone or an aldehyde using our hydride-based reducing agents, lithium aluminum hydride or sodium borohydride? So go ahead and pause it and see if you can come up with the 3 reactions that are really different reagents that do a very similar overall reaction. Okay, let's go ahead and talk about, right, and review those reactions so that they kind of exist in our mind together. So in the last chapter, we learned about the Clemmensen reduction, right, and which is typically done after acylation of an aromatic compound, right? So after acylation, using Friedel-Crafts acylation, we can do a Clemmensen reduction that utilizes a zinc mercury amalgam with HCl and reduces the carbonyl completely, right down to an alkane. So again, this one is called the Clemmensen reduction. Okay, we also learned in this chapter about the Wolff-Kishner reduction. I don't know why I'm drawing an aromatic ring. I think I just got carried away from the first case, but let's say it could be any carbonyl, right? So let's say we'll place it in a different position just to show that it doesn't need to be at the benzoic carbon. The Wolff-Kishner reduction is a two-step synthetic process. The first step utilizes hydrazine, which is NH2NH2, right, to form hydrazone. It's done under acidic conditions and we lose water in that process, followed by aqueous potassium hydroxide and heat, right? That will reduce a carbonyl all the way down to an alkane. Right, we'll label that one Wolff-Kishner reduction. Right, and please don't get married to this exact example. Could be any carbonyl for these reactions. So just because I'm drawing these are specific examples doesn't mean that it only works in this exact substrate, for example. Okay, and then the last one we just looked at is the Raney nickel reduction, right? So if you take a ketone and you form a thioacetal, and it's common to form a cyclic thioacetal under acid catalyzed conditions, right? And then treat that with Raney nickel. Right? We will reduce, again, the carbonyl all the way down to an alkane, right? And we're going to call this the Raney nickel reduction. It's not really a name of a chemist, but that's what I'm going to call it. Okay, and over here, we can compare and contrast those to the reduction using lithium aluminum hydride and sodium borohydride. So for example, remember that if we reduce a carbonyl with either lithium aluminum hydride or sodium borohydride, right, we end up with an alcohol. So it doesn't completely reduce the carbon. Instead, we end up only partially reducing it down to an alcohol. Right, and this, of course, would be a racemic mixture of that alcohol, but the reduction does not yield a CH2 group. And that's the difference, right, between those and the other reductions that we were talking about. Okay, going back to the slides. Right, this slide is a nice review of your hydride reducing agents and how those give you alcohol products. The mechanism is consistent with the basic condition mechanism, right? Because hydride is a strong nucleophile, so it's the basic conditions and also a strong base, right? Where the hydride will directly attack the carbonyl carbon. There's no acid, right? There to protonate it first, and then we protonate the resulting alkoxide, and that gives us our alcohol product. Right, let's look at those mechanisms. So again, this is a review mechanism from a previous chapter. I believe it's chapter 12 or 13, depending on the edition of your book. Hydride from either sodium borohydride or lithium aluminum hydride does a nucleophilic attack on the carbonyl carbon. Electrons go up to the oxygen to form the tetrahedral intermediate, which gets protonated by a proton source. Could be the solvent in the case of sodium borohydride, or water getting added to the reaction at the end of the reaction with lithium aluminum hydride, giving the alcohol product. Just a note that if you end up generating a chiral center through reduction, you will always get a racemic mixture. There's nothing influencing the hydride from attacking from one face or the other face of a planar molecule, and it'll be 50-50, resulting in a racemic mixture. The Grignard reagent is also a review reaction. The Grignard is a strong nucleophile and a strong base, so this is consistent with basic condition mechanism, right? Where the Grignard does a direct nucleophilic attack on an aldehyde or ketone. After proton transfer in the second step, we end up with an alcohol product, and we've also formed a new carbon-carbon bond, which is the highlight of the Grignard reaction. And again, if we end up forming a chiral center, it will be a racemic mixture. Right, so this is the mechanism of the Grignard reaction: nucleophilic attack of the Grignard reagent, formation of the tetrahedral intermediate, and proton transfer from the workup provides the alcohol product. Another carbon-based nucleophile is cyanide. Right, we can use cyanide, which has a carbon with a formal negative charge. It is a nucleophilic carbon and can do a nucleophilic attack on this electrophilic carbon. And when it does, it forms a product that we call a cyanohydrin. The mechanism works better under basic conditions, so typically catalytic base is used, which basically means even though a stoichiometric equivalent of HCN is used, typically a small amount of potassium cyanide is also added. That allows for nucleophilic cyanide to be present and do its nucleophilic attack on the carbonyl. This is reversible because this is also a good leaving group. And then no need to add an acid workup because HCN has an acidic proton that will allow for the protonation of the negatively charged oxygen to form a neutral intermediate. Again, it's reversible, and we would play around with conditions, for example, using a large excess of one of the reagents to drive the reaction to the formation of the products. So here are some examples. Notice some catalytic KCN, it doesn't say that, but that's usually the way it works, and a stoichiometric HCN getting added, formation of the cyanohydrin. And again, it's common to form a chiral center, in which case it will always be a racemic mixture. What we're going to do is in the next chapter, we'll explore the reaction of nitriles or cyano groups, right? So for now, we'll suffice it to say that this is a useful functional group that will allow us to convert to many other types of products. So for example, we could reduce the nitrile using LAH to get an amine, or you can do a acid catalyzed hydrolysis using heat of the nitrile to get a carboxylic acid. So those are some other functional groups we can access from the cyano, also called a nitrile functional group, and that those reactions and more will be explored in the next chapter. Another carbon-based nucleophile is an ylide, also known as a Wittig reagent, in what's called the Wittig reaction. Okay, notice how I'm pronouncing it, right? This is a German name, and so it's not Wittig, it's Wittig. And it's an extremely important organic reaction, it's a named reaction. It does form a new carbon-carbon bond, but even more specifically, it actually forms a new carbon-carbon double bond, right, from a carbonyl and this ylide, also known as Wittig reagent. So the carbon skeleton is modified by the formation of the new carbon-carbon double bond. Ketones or aldehydes are converted to alkenes, right, with the formation of a new carbon-carbon double bond. So very, very interesting, very useful reaction for an organic chemist. It utilizes a specialty reagent, kind of like the Grignard reagent, but it's not exactly a Grignard reagent, it's different. And so sometimes it's called the Wittig reagent or a phosphonium ylide. So the Wittig reagent or phosphorus ylide is resonance stabilized. Sometimes you'll see a double bond being drawn between the carbon and phosphorus. And sometimes you'll see it where the electrons are on the carbon. from the bond, leaving a carbanion next to a phosphorus cation, right? So they're stabilized by the opposite charges next to one another. And it's kind of like a Zwitterion, okay, but it's called an ylide. The definition of an ylide is a neutral compound that contains a negatively charged atom adjacent to a positively charged heteroatom, which is a little different from a Zwitterion, which can be any atoms, right? Where in this case, we need a heteroatom that's positive charged next to a carbon that's negatively charged. So the carbon specifically is important to call it an ylide, whereas it could be any atoms like oxygen and phosphorus, for example, or oxygen and nitrogen, to call it a Zwitterion. And they don't have to be right next to each other when you call it a Zwitterion. But with an ylide, the positive and negative do need to be adjacent to one another. Okay, if you think about which one is the more stable resonance contributor, you might think, well, this one is neutral, right? Shouldn't that be more stable? But remember that this pi bond is formed from overlapping p orbitals. And carbons is going to use a 2p orbital. Phosphorus is going to use a larger 3p orbital. It's going to be a mismatched orbital size. And so their overlap is going to be weaker, and resulting in not a very strong pi bond. So it's actually thought that this is the contributor that most, the true structure most resembles. Okay, the mechanism that we're going to draw for the Wittig reaction is going to involve a 2+2 cycloaddition. Remember, we saw those in the chapter that contained the Diels-Alder reaction, which was a 4+2 cycloaddition. But this one's going to be a 2+2 cycloaddition between the Wittig reagent and the carbonyl group. So what would that look like? Depending on the resonance contributor you use, you can either start on the anion on the carbon to attack the electrophilic carbon of the carbonyl, or if you had drawn a pi bond here, then you would have started your arrow on that pi bond to attack the carbonyl carbon. Either way, the electrons from between the pi electrons between the carbon and oxygen here, which spend the majority of their time around the oxygen, would then go and attack the phosphorus simultaneously, essentially doing a 2pi plus 2pi cycloaddition, generating a 4-membered ring, which we call an oxyphosphatine intermediate. This is obviously high energy intermediate because of the 4-membered ring, and will immediately fragment to do what's called a retro 2+2 to form a carbon-carbon double bond, or alkene, and triphenyl phosphorus oxide. Triphenyl phosphine oxide, excuse me, which is the byproduct. It's a very convenient byproduct because it precipitates out of the solvent that's used, and so it can easily be filtered out of the reaction. So, and you'll see this reaction done in the lab to see the utility of that. But overall, we have the conversion of a carbonyl to an alkene, which is very, very useful. Okay, how do we make that Wittig reagent, right? We went to the trouble when we talked about the Grignard reagent to talk about how it's made, right? You start from an alkyl halide and you treat it with magnesium metal. So we want to talk about how do we produce that Wittig reagent, that ylide. So it's a 2-step process, and it does also start with a alkyl halide. Unlike the Grignard reagent formation, we can't use any organo halide. So the carbon must be sp3, okay, so it cannot be like a phenyl ring or something. Cannot be sp2. And it needs to be unhindered, okay? Ideally, it's unhindered because we're going to be doing an SN2 reaction with triphenyl phosphine. So think of phosphorus as like nitrogen. It has an available lone pair that it can use to donate to an electrophile. So we can do a nucleophilic attack and loss of a leaving group, essentially an SN2 reaction, to form what's called a phosphonium salt. And then because the phosphorus is positively charged, it makes the protons on the alpha carbon more acidic, and we're able to deprotonate them with a strong base. And a common base that's used would be N-butyl lithium, which stands for normal butyl lithium. Think of this as like a Grignard reagent. It's a very strong base. With a Grignard reagent, we would have a carbon magnesium bond, but a carbon lithium bond is almost analogous to a carbon polarized bond, and the carbon has significant anionic character. So not only is it a strong base, but also a strong nucleophile. So we would not be able to use this in the presence of a carbonyl, because it would just attack a carbonyl like a Grignard attacks a carbonyl. But there's no carbonyl here. All there are acidic protons, so we can do a deprotonation to form the Wittig reagent. So 2 steps: from an alkyl halide that's ideally unhindered, treatment with triphenylphosphine to form the phosphonium salt, deprotonation with butyl lithium gives us the ylide, also known as the Wittig reagent. The Wittig reaction is stereoselective, meaning that you can favor the formation of a Z or E alkene depending on the Wittig reagent used. So if you have just an alkyl group attached to this carbon, then we call these unstabilized ylides. And when you used an unstabilized ylide, the Z alkene is formed. And the reason that the Z alkene is formed, because you know that this is obviously not the most stable alkene product, it's thought to be kinetically controlled, where the first 2+2 cycloaddition is irreversible. And the formation of the more stable, lower energy pathway to the intermediate is then trapped because the reaction is irreversible. And the reason it's irreversible is because unstabilized ylides are not stable, so they're not likely to act as a good leading group. Whereas in contrast, if you use a stabilized ylide, stabilized ylides attached to this carbon, instead of just an alkyl group, we actually have an electron withdrawing group, or something that can stabilize an anion on this carbon through resonance. So, and the better that it stabilizes the anion through resonance, the more stabilized it is, and the more it will produce the E alkene product. This is the more stable product, and it's thought to be produced through a reversible initial 2+2 cycloaddition that eventually leads to the more stable product through a favorable equilibrium. An anion here would be resonance stabilized through a ring as well. So this is considered a stabilized ylide, producing the E alkene as the major product. However, it's not as stabilized as using an ester as an electron withdrawing group, because the anion in this case is stabilized up to the oxygen of the carbonyl as alone. And in this case, the anion is stabilized only on 3 different positions in the ring on carbons, which is not as stable. And again, this will be studied in the lab, particularly if you're taking me for the lab or a lab at Miramar College. Okay. Let's talk a little bit about retrosynthetic analysis for the use of the Wittig reaction. If you're trying to think about how can I make this alkene through a Wittig reaction, then we know that we make the carbon-carbon double bond through the Wittig reaction, and we make it from a carbonyl on one side. So that could be this ketone or this aldehyde, depending on which side gets the carbonyl. And the other side is the Wittig reagent, which we form from an alkyl halide. So breaking it up, this carbon-carbon double bond apart retrosynthetically leads us to 2 possible routes, right? Either we have 2-butanone and the Wittig reagent with a small alkyl group, CH2 here, or formaldehyde and a Wittig reagent formed from a more bulky carbon-based group, right? So that's going to be route number 2. So let's consider which route is better by thinking about how do we actually access the Wittig reagent in the first place. The Wittig reagent, again, is made through that 2-step process where we take an alkyl halide, treat it with triphenylphosphine to form the phosphonium salt, and N-butyllithium to deprotonate it to form the Wittig reagent. And remember that I said that less hindered alkyl halides are ideal because the first step utilizes an SN2 reaction. So this is a much better route because methyl halide is much better than a secondary alkyl halide, right? So this is a much more easily accessible Wittig reagent, which means that pathway 1 that we had talked about before is the ideal pathway. And we would then use 2-butanone as the carbonyl component to form that alkene in the forward direction. Okay, let's do a practice problem where we want to think about how we might make this carbon-carbon double bond through use of a Wittig reagent. I know it says and HWE, which stands for Horner-Wadsworth-Emmons. Sorry, please, I forgot to just erase this. We are skipping Horner-Wadsworth-Emmons reactions, so just disregard that in the title. Okay, so we're looking for a synthetic path to form this alkene, probably through a Wittig reagent, since Wittig reaction, since that's what we were just talking about. So think about, I'm going to be converting this alkyl halide to an ylide. Is that compatible with the ketone, or might I need to do something with this ketone first? So I'll let you think about that, and then we'll talk about it. Go ahead and pause it if you need a little bit more time. Otherwise, we're going to go right into talking about this. We're going over it. Okay, so let's think about if we were to convert this alkyl halide, which is primary, that's good for an SN2 reaction, into an ylide or a Wittig reagent, we would first treat with triphenylphosphine and then treat with N-butyllithium. That's a bit of a problem, right? If we use N-butyllithium in the presence of a ketone, what's going to happen? Essentially, the Grignard reaction is going to happen, and the butyllithium will attack the ketone. So in order to avoid that happening, we can actually protect the ketone, right? So remember that a protecting group for the ketone that's useful is an acetal, because the acetal is going to be stabilized under basic conditions. So it is not going to react under basic conditions. So first step is going to be putting on that acetal protecting group. So we're going to use a diol, acidic conditions, and minus water to form the acetal. Now this carbon is protected under basic conditions, nothing will happen to it. So now we can do our two-step process to form the ylide, which is needed for the Wittig reaction. So first step is triphenylphosphine. The second step is the butyllithium. So let's then incorporate that ylide into our product here. Right, so we are going to form, and you can draw either resonance contributor for the ylide that you want to. So you can either draw the double bond, or you can draw the carbon with a lone pair and an anion, and the phosphorus with a positive charge and just a single bond between the carbon and phosphorus. Right, so we were able to convert this using strong base and butyllithium, right? And we didn't touch this carbon, so that's an because it was protected. But now we want to react it with the ylide, so we want to go ahead and deprotect that and reveal the ketone again. Make sure that you didn't add any carbons, right? We shouldn't have done that in the formation of the ylide. Okay, so the deprotection conditions for the acetal are dilute, right, H2SO4. And now we're going to reveal the ketone, and it's going to be able to react together, right? You can think about sort of zipping those two carbons together and losing the other as triphenylphosphine oxide. Okay, so this is going to be a 1, 2, 3, 4, 5, 6-membered ring, right? Which is perfect because that's our product, a 6-membered ring, right? Those should just react together in the, after this is revealed, they'll immediately react together. Right, so we'll just kind of put some brackets because this is not isolated, okay, in the Wittig reaction. Okay, so there you go. Let's get back to the slides. All right, the last reaction in this chapter is the Baeyer-Villiger oxidation, and it's a oxidation because the carbonyl carbon ends up oxidized. Specifically, it either ends up as an ester or a carboxylic acid, and that carbon is more oxidized than the carbon of a ketone or an aldehyde. So what happens is the reagent is MCPBA, or a peroxybenzoic acid. So of course, if there was an alkene there, that would also form an epoxide. But MCPBA has more utility than just forming an epoxide using an alkene. We can also use it to react with a ketone or aldehyde. And it will insert an oxygen in between one of the carbon-carbon bonds, or could be a carbon-hydrogen bond, to either again form an ester or a carboxylic acid. The mechanism, so this is the peroxybenzoic acid, and this could be MCPBA, right? That's a common peroxybenzoic acid that's used. If it was MCPBA, this would be a phenyl ring with a metachloro, because the MCPBA stands for metachloro peroxybenzoic acid. But either way, the oxygen of the peroxybenzoic acid, the one that's not resonance stabilized with the carbonyl oxygen, the more nucleophilic oxygen does a nucleophilic attack on the carbonyl of an aldehyde or ketone. That forms a tetrahedral intermediate. This is an intramolecular proton transfer that's happening because this is already hydrogen bonding, right, in a 5-membered ring-like transition state. So it's really easy for this to reach around and grab this proton because it's basically a 5-membered ring transition state. So after a formal proton transfer, a very unique reaction occurs due to the labile or weak oxygen-oxygen bond that's easily broken. One of the carbons can migrate over to the oxygen, breaking this bond and sending electrons up to this oxygen. This is a great leaving group, right? Because it's essentially a neutral carboxylic acid. And in order to regenerate a carbonyl between this carbon and oxygen with these electrons, something has to leave. And interestingly, we can do a shift or a rearrangement, right? Essentially a methide or an alkyde shift or a hydride shift, right, occurs onto this oxygen while simultaneously breaking that bond. Very interesting mechanism, and I go through it a little slower and step by step in a YouTube video. So please go ahead and watch that one at your convenience. And if you use a ketone, for example, a cyclic ketone, then when you insert an oxygen between the carbon-carbon bond, you're going to end up with a cyclic ester, which is also called a lactone. So that's a new functional group name for you, right? And again, the reagent is some sort of peroxybenzoic acid, which commonly you might see MCPBA. So this one is, we don't have to care about regioselectivity because there's an internal plane of symmetry, right? So it doesn't matter if we insert between this carbon-carbon bond or this carbon-carbon bond, you end up with the same product, right? But what if it was an aldehyde or an unsymmetrical ketone, right? Then the carbonyl carbon is attached to different things on each side. So we then need to know, okay, which side group migrates faster. And so we can use it's been experimentally determined to have this migratory pattern. where a proton or a hydride shifts fastest, followed by a tertiary carbon. Secondary and phenyl have about the same rate, then a primary carbon, then a methyl. So you can use this order to determine the regioselectivity. Let's look at a couple of examples. Right, if you were inserting an oxygen into one of these carbon-carbon bonds of this ketone, does it insert between this carbon-carbon bond, or does it insert between this carbon-carbon bond? So we would use this migratory pattern to predict that. This is a secondary carbon, right? And this is a methyl group. Okay, so we have, if we look and see, okay, this is going to be faster. So we're going to insert between that carbon and this carbon, right, to make this particular ester, as opposed to inserting between this bond and making a different ester. What about this aldehyde, right? Aldehydes have a hydrogen attached to the carbonyl carbon, and the hydrogen migrates the fastest. So we're always going to insert between this carbon-oxygen bond and end up with a carboxylic acid product. So whenever you use an aldehyde, you always get a carboxylic acid. But when you use a ketone, if it was cyclic, you might get a lactone, right? And if it's acyclic, you get an ester. And if it's asymmetric, then you need to figure out which carbon will likely migrate faster and insert the oxygen into that carbon-carbon bond. Okay, let's talk about some synthetic strategies. Whenever you are dealing with a synthesis problem, you should be asking yourself two questions. Is there a change to the carbon skeleton? And is there a change in the functional group? If there is a change to the carbon skeleton, think about what reactions are available to you. In this chapter, if you're making a new carbon-carbon bond, the likely reactions are a Grignard reaction, cyanohydrin formation, and or the Wittig reaction if you want to generate a carbon-carbon double bond. So let's look at an application problem, right? Think about how you would devise a successful multi-step synthesis to achieve this transformation. Okay, so think about, is there a change in the carbon skeleton? If so, which reaction do I want to use? Do I want to use a Grignard? Do I want to use cyanohydrin formation or a Wittig reaction? And think about how you would manipulate the functional groups shown. Go ahead and pause it if you need to think about it, and then we'll talk about the answer, or at least one possible answer to this question. Okay, so when I ask myself, is there a change to the carbon skeleton, right? Well, I have the phenyl ring, and then I have 2 carbons. And over here I have the phenyl ring, and then I have 3 carbons. So the answer is yes, there's a change in the carbon skeleton. In addition, there's a change in functional groups because we're going from a terminal alkyne to an alcohol. So the answer is yes to both questions, but because there's a change in the carbon skeleton, I want to ask myself, do I want to utilize a Grignard reaction, or do I want to utilize cyanohydrin formation or a Wittig reaction? So you can think about what one would be best, and there might be multiple answers that are correct. But what I am thinking about doing actually is exploring my options from a terminal alkyne, right? And then after I do that, I'm going to think about what carbon-carbon bond skeleton changing reaction I want to use, right? So one of the things I know about a terminal alkyne is that I can access either a aldehyde or a ketone from a terminal alkyne. Those are part of the review reactions for this chapter. So it's quite possible that I could convert this to an aldehyde or a ketone, right? And if I convert it to an aldehyde, I'm going to get this aldehyde. And if I convert it to a ketone, I'm going to get a methyl ketone, right? So right now I'm simultaneously exploring 2 possibilities, and I'm not sure which one I want to use. And that's okay, right? As thinking about different potential routes at the same time. The reaction to produce a terminal alkyne from, an aldehyde from a terminal alkyne is the 9-BBN, right, followed by sodium hydroxide and hydrogen peroxide. And the reaction to produce a methyl ketone is a H2SO4 and water, and mercury sulfate is a catalyst. Okay, so those are review reactions that I memorized, right? And I might think about now, I know I need to add another carbon and eventually get an alcohol functional group. Which one of these is more useful for me at this point, right? So at this point, I kind of like this ketone because of this methyl group, right? I'm looking at this methyl group and it kind of reminds me of this methyl group, right? So this might be something that I pursue a little bit more. The aldehyde is okay. The problem is I can definitely imagine this aldehyde becoming this primary alcohol, but how am I going to get a carbon here, right? Not extremely easily. It's certainly possible maybe to go through an epoxide or something, but even a Grignard wouldn't attack this carbon. It would probably attack the less substituted carbon. So it's going to be difficult to get a carbon attached to this carbon. There's ways to do it, but we haven't covered those reactions yet because those are the reactions from a subsequent chapter that we haven't talked about yet. So right now, with the reactions that I have available to me in my brain, I don't know how to put a methyl group here, right? Again, it's very possible to do, but I don't know how to do it yet. So I'm thinking kind of about this ketone a little bit more, right? And I'm thinking, okay, how could I get a carbon here? Well, I could get a carbon here through a Wittig reaction. And that's really attractive to me right now. What if I convert this to an alkene and I make this a carbon, right? In that process, I will have added my additional carbon. So I'm thinking about the use of a Wittig reaction, specifically to convert that carbonyl into an alkene, which will give me an extra carbon that I need. Right? I can certainly do this Wittig reaction. I need an ylide to do that, right? So I'm just going to use the very common ylide with just a CH2 group attached to the triphenyl phosphine. And then from here, I can convert that alkene to an anti-Markovnikov hydrate product, right, through use of hydroboration oxidation, which utilizes BH3THF and hydrogen peroxide and sodium hydroxide in the second step. Okay, so that's one option. There may be other options, but this is one possible pathway. Right here, this kind of led me to a dead end, so I just abandoned that route. All right, going back to the slides and moving on. Let's talk a little bit about spectroscopic analysis of aldehydes and ketones. So if we talk about infrared spectroscopy first, one thing to note is that typically for ketones, we see the carbonyl absorption band around 1715 wave numbers. And the absorption moves into the fingerprint region or very close to it. And when the carbonyl is conjugated, and that's because if we draw out the resonance contributors, we'll see that there's additional and greater single bond character between this carbon and oxygen than when that extra conjugation is not there. So it reduces the wave number of the carbonyl absorption stretch. Aldehydes also give weak peaks around 2700 and 2800 for the CH stretch that's unique to an aldehyde, right? So around a little to the shoulder of our normal carbon that's sp bonded to hydrogen stretch, we see two additional bands for this particular carbon-hydrogen bond that's only exists in aldehydes, and that's something to look for if you think you have an IR of an aldehyde. let's talk a little bit about NMR analysis, right? So aldehydes are very diagnostic in an NMR because the hydrogen of the attached to the carbonyl carbon is downfield, very downfield, typically between 9 and 10 ppm. So that's very, very telling that we have an aldehyde in the NMR. In addition to that, hydrogens that are alpha to a carbonyl are shifted by about 1 ppm, right, from where they normally would be if that carbonyl was not there. So they typically appear around 2 to 2.5 ppm. If you look at a carbon-13 NMR, carbonyl carbons, right, show up very, very downfield, around 200 ppm. So that's telling that we likely have a carbonyl if we see a signal all the way downfield at that chemical shift. Okay, the last slide is just a review of reactions. There was lots of reactions covered in this chapter. A lot of these reactions are reversible. I'm not sure they show the reversible arrow for hydrate formation, but they should also show it for acetal, cyclic acetal, thioacetal, imine, enamine, oxime, hydrazone formation. All of these reactions are reversible. The hydrazone is useful because we can treat that with hydroxide and heat and do the Wolff-Kishner reduction to get an alkane. And we can also reduce a thioacetal using Raney nickel down to the alkane. So those were reactions covered in this chapter. Review reactions were hydride reduction of carbonyls to alcohols, Grignard reactions of carbonyls to form alcohols with new carbon-carbon bonds. New to this chapter was cyanohydrin formation, the Wittig reaction to form an alkene, and the Baeyer-Villiger oxidation to form a carboxylic acid or ester. Right, so make sure that you are studying these in whatever way that you find best, maybe flashcards, to get you started and practicing lots of mechanisms, both in forward and reverse direction, and practicing synthesis problems, and remembering that in synthesis, sometimes we need to protect the ketone or aldehyde. It's carbonyl, and so utilizing an acetal is helpful for that. Okay, I will see you guys later.